Welcome to another video of Beta CAE Systems. In this video, we demonstrate Bolt Assessment, a dedicated tool to be used for fast evaluation of bolted joints failure according to commercial or user-defined standards. Using the tool, bolt failure can be evaluated according to VDI 2230 and Eurocode 3 standards. In addition, bolt data and forces can be extracted and applied to any other commercial or user-defined criterion of bolt failure. To properly use the tool, the geometry and results files need to be imported in Meta. Bolts of 1D and 3D representation are automatically recognized by the tool from the geometry only. Thus, any preprocessor can be used to create the model. Primarily, displacements must be read from a static, implicit, or explicit simulation. In addition, grid point forces data should be available in the results file, at least for a set containing all elements of the bolts in the model. From the individual nodes of a bolt cross-section, the average forces and moments can be found. In general, the tool evaluates grid point forces from Applicis, Nastran, Abaqus, LS-DYNA, ONSYS, and PAM crash solvers. Using the tool, counterplots showing the safety status of the bolts can be created on the model. Besides, a report summary is also available showing the values of each failure mode according to the standard used. Moreover, detailed reports with analytical hand calculations can be generated in PPTX or XLSX format. Additionally, the full history of the bolt's internal forces and moments can be created to give you insights about the loading condition of the bolts. Finally, algorithms determining the required bolt diameter and class to prevent failure have been implemented. The model under investigation features an axle connected to the pulleys using 3D bolt representations. While the pulleys are fastened to each other using 1D beam element bolts. Tension and torsion are applied to the right end of the axle, causing the solid bolts to experience shear and the beam bolts to withstand mostly axial forces. During the pre-processing stage in ANSA, a set containing all bolt elements was created to request grid point forces from the solver. This set can also be used to isolate all bolts. The bolt assessment functionality can then configure the bolts based on geometry and connectivity and create internal bolt entities in Meta. Pretension is a crucial factor in bolt design. The tool allows you to either manually apply a pretension axial force if it has not been modeled, or extract the pretension force directly from the solver results if it has been included in the model. In this example, pretension will be artificially added to the bolts using the Eurocode 3 formula. Access Bolt Assessment Tool from Analysis, Durability Ribbon. The tool can be found in the Special group. Click the Bolt Assessment icon to open the tool. Alternatively, type Bolt Assessment in the search engine of Meta. All tools can be docked and undocked next to the database browser for better handling. Drag the tool and place it next to the Database tab to dock it. Double-click on its name to undock it. To run a bolt analysis using the tool, it is not mandatory to read all states. Find the last state from the list where all forces have been fully applied and select it. Read displacements and optionally scalar results, for example von Mises stresses, and import the results in Meta. Change the fringe settings to on node in order to observe the nodes exhibiting the maximum nodal scalar value per bolt. The location of the maximum nodal scalar can be used to create a cross-section and extract the forces and moments of the bolts. Having the bolts as the only visible geometry of the model, click the Bolts from Visible button to initiate the process of configuring the bolt entities. Apply a basic name for the bolts and click OK. Briefly, based on each bolt orientation, the tool will internally create sets, cut planes, and coordinate systems to extract the section forces and moments from the bolts. Grid point forces will be converted to axial and shear force, as well as bending and torsion moment at the cross-section. A list with all bolt data has been generated in the tool and facilitates the necessary input parameters to analyze the bolts according to the selected standard. In this case, Eurocode 3. Note that the diameter of each bolt has been automatically identified from the geometry. Therefore, the bolts must be modeled correctly in the pre-processing stage. All parameters of the bolts can be edited before and after calculations. Click the Edit List button and manually change the parameters of interest. For example, all bolts should have washers. Type Yes and press Enter to edit all rows in the list. Each row represents a single bolt. Click OK to save the changes. When the definition of the single bolted joints is complete, switch to the Report tab of Bolt Assessment tool. Before running the analysis, it is better to show only the bolt entities and enable the line elements cross-section in order to observe the failure contour plots clearly. Click the Report Summary button to initiate calculations and evaluate the safety of the bolts. One label has been created per failure mode as declared in the Eurocode 3 standard. In addition to the contour plots, a report summary list is generated, showing all failure modes per bolt. The list can be sorted by the user based on each failure mode. Sort the list using the overall to examine the most critical bolt on the model. The overall considers the worst value of all failure modes. Sort the bolts using the shearing failure mode in order to identify the bolt with the worst shearing condition. When the bolts are configured from visible, each bolt entity is assigned a unique internal ID. You can sort the list based on these IDs. To generate a detailed report for all bolts, select all items in the list and click the Report button. It is possible to create a report for either the selected bolts or the failed ones. This action generates a report in PPTX format, with each slide dedicated to a single bolt. The left table on each slide displays all input data, including bolt dimensions and properties, as taken from the library based on the nominal diameter of the examined bolt. Additionally, the cross-sectional forces and moments, as well as the assumptions used for pretension and joint design, are presented. The right table provides analytical calculations for all Eurocode 3 failure modes. For clarity, each slide also includes an image illustrating the reported bolt. When designing bolts, it is essential to discover the appropriate diameter to meet all failure mode criteria of the standard. Click the corresponding button to initiate the algorithm that determines the required bolt diameter and class to prevent failure. The algorithm predicted that all M16 bolts of class 8.8 should be replaced with M22 bolts of the same class. Moreover, the old and new overall values are reported for reference. In the Settings tab of the tool, enable the option to consider different classes through the iterations of the algorithm. Rerunning the algorithm having this option enabled will predict bolts of smaller diameter but higher class. In this case, M20 bolts of class 10.9 can be also used to prevent failure according to Eurocode 3. Understanding the loading history of the bolts from the first to the last state is crucial when designing bolted joints. For that reason, the Bolt Assessment tool provides this feature. To generate the history of section forces and moments, select the bolts of interest from the list and click the corresponding button. This will plot the axial, shear, bending, and torsion forces of the bolt as curves. Use standard 2D plot functionality of Meta to examine the created curves. A closer look to the axial force of the bolt can indicate separation of joints where a steep increase is observed. Joint separation induces higher internal forces in the bolt as a result of bending, an effect also called as prying action. Editing the single bolted joints list allows the user to conduct what-if studies. All parameters in the list are editable. For instance, you can change all M16 bolts to bolts of M22 diameter as recommended by the design algorithm. Rerunning the analysis and reviewing the overall safety factor, you can confirm that bolts meet the safety requirements. After completing all investigations, you can restore the list to its initial state. Simply click the Refresh button to revert the list to its original values. You can start a completely new analysis by configuring other bolted joints of the model. In this case, users may delete the internally created entities, such as bolt sets, coordinate systems, and cut planes, from the database. Then, restart by adjusting the options for the bolted joints definition and click the Bolts from Visible button. In the following example, 3 states have been imported into Meta. The bolt section forces and moments will be extracted from the last state, while the pretension axial forces will be taken from the first state. In this scenario, pretension has been modeled to establish contact with the plates and is fully developed in the first state. From the Settings tab, change the preload consideration to the option Preloads will be exported from the pretension state. and declare the state ID 1 at the respective field. Click the Bolts from Visible button to configure the bolt entities. As usual, apply a name for the bolt sets and click OK. When the process is finished, 5 new bolts appear in the list. In the last column, the pretension force extracted from the solver is assigned to each bolt. Moreover, the axial force extracted from the last state already includes the pretension force as well as the additional bolt working load from the external forces acting on the joint. For applications requiring preloaded bolts, the correct approach is to model pretension to establish contact between the plates and then extract the pretension as axial force using the tool. This ensures the most accurate results and reports. However, in the initial design stages, users can import bolted joints without pretension, typically using 1D bolt representations, to quickly estimate the appropriate number and diameter of bolts needed for a proper joint design. From the Settings tab, you can choose to perform calculations and generate reports using safety factors, safety margins, or utilization factors. By default, the tool calculates safety factors as stated in Eurocode 3. However, you can change the output type to your preferred format. Unlike safety margins, safety factor values below Unity indicate a safe failure mode. Utilization factors represent the safety factors multiplied by 100%. In all cases, the fringe bar is updated accordingly to reflect the correct coloring of safe and failed bolts.